All right, we're going to revisit the tank filling problem. And this time we're going to add a sink to the tank. And to make it interesting, we'll assume that the outflow, the flow rate out of the drain, is going to be a function of the height of the water in the tank. So if the height is very high, that'll exert a higher pressure at the bottom of the tank where the drain is, and it will drain faster. Whereas if the water level is very low, the pressure will be very low, and then the drain will be slower. So in a picture, our setup is the following. We have the tank, and we put a drain at the bottom, and there's going to be some water level H, and the outflow, flow out, is equal to some constant alpha times H. So the constant alpha is greater than 0, and the dimensions of alpha is length squared over time, so that alpha times H as dimensions of length cubed over time, so for an outflow. And we'll keep the same flow in as before, flow in, and that will just be a constant R. And now if we do the conservation of the volume, dV dt is equal to flow in minus flow out is equal to R minus alpha times H. And on the left hand side we have V, on the right hand side we have H. So we can either replace this by some expression in terms of the volume, or we can replace this one in terms of the height. So we know that we're going to assume in this case that the volume is equal to H times V. So V of T, the volume is equal to H times a cross-sectional area, A. And A is a constant. A is constant. In other words, the sides of the wall are perpendicular to the bottom, and it's a rectangular prism, so as the water level increases, the area doesn't change. As opposed to if you had a cone, for example, if you had a conical tank, then as the water level fills up, the cross-sectional area increases, and as it drains, it decreases. So we're not going to do this case. Interesting, but not the one we're solving. So A doesn't depend on height. And so with this, I can now simplify the equations. A times dH dt, right? A is a constant, so I could take it out of the derivative, is equal to R minus alpha H. Or, rewrite one more time, dH dt is equal to R over A minus alpha over A H. And to this, to make a proper problem, we need to give it an initial condition, and we're going to assume that the initial condition is at time t equals t naught. So H of t naught is equal to H naught. This is the initial condition. So we could in principle start off the problem with a finite H naught, let's say 1 meter, and then see what happens. Does it decrease or does it increase? And that'll depend on whether the flow in is bigger or smaller than the outflow. If what H is 1 meter, the inflow is bigger than the outflow, then the water level will increase. If the outflow is bigger than the inflow, then the water level will decrease. All right, so let's solve this equation analytically first, and then we will go back and do it numerically. I think it's useful to do some problems where we can solve both ways to see what's going on. And so the way we're going to solve it is in terms of a homogeneous and a particular solution. So when we have a problem where one term here depends on the dependent variable, H, and the other one does not, one method of solution is to look for a solution H, which is equal to one part which is the homogeneous solution, plus one part which is a particular solution. And the particular is any solution that makes the equation correct. And for a simple equation like this, where RA and alpha A are all constant coefficients, and h appears only linearly on the right hand side, then it's usually pretty easy to guess at the particular solution. And so the idea is that the particular solution will take care of the inhomogeneous term, and then the homogeneous solution is the one where we solve the equation by ignoring this term here that doesn't depend on h. So that would be the homogeneous one. So the equation for the homogeneous equation is the following. Homogeneous solution. We solve this equation: d h homogeneous dt is equal to minus alpha over a h homogeneous. And the particular solution is anything that satisfies the equation. So in particular, we can look for a constant solution. So if hp is a constant, then the left-hand side will be 0, and we'll just have 0 is equal to r over a minus alpha over a times hp. And then this is a simple equation to solve to get the particular solution. So let's work it out right now. The particular solution is hp equals constant. And if I substitute this in the equation, dc dt is 0, so I get 0 is equal to r over a minus alpha over a c. And from here I can solve for c. c is equal to a over alpha times r over a is equal to r over alpha. So hp is just r over alpha. So this was pretty easy to get the particular. And now we have to solve the homogeneous one. Now we can't just integrate both sides, the left and the right, because the right hand side depends on h, and we don't know h yet, so we can't do this integral. So this is different than the previous problem, in which we just prescribed the source and it didn't depend on the volume of water in the tank. Now it does. So one way of solving this kind of problem is to do what's called separation of variables. So we end up with this dh homogeneous over h homogeneous is equal to minus alpha over a dt. So we multiply both sides by dt, eliminate the dt, and divide both sides by hm to eliminate hm and get on this side. And now this left hand side depends only on h, whereas the right hand side depends only on dt, and so we can now integrate both sides. So if we integrate both sides, what we get is log of h homogeneous is equal to minus alpha a t plus some constant, which I'll specify in a little bit, but it will always be the case that the constant of integration will show up in the homogeneous part of the equation. So once we have the homogeneous part, we're going to have an arbitrary constant that we can use to satisfy the initial conditions. Right, this one is just determined. We'll take care of the non-homogeneous part, but has no free parameters, whereas this one will have this constant of integration. So the next step is to exponentiate both sides to get rid of the log. This will give us h homogeneous is equal to the exponential of minus alpha over a t times, right, if I exponentiate, or I could have plus the constant, but the exponential of a plus b is the exponential of a times the exponential of b, and the exponential of a constant is just another constant, which I can put out front here, b. So this for b is constant, and it's remains to be determined using the initial condition. So let's solve for what b shall be now. So with our solution is h of t is equal to h homogeneous of t plus h particular of t, which is b exponential minus alpha over a times t plus r over alpha. And now we to get the initial condition, to solve for b, we use the initial condition, so we substitute t equals t naught and we set it equal to h naught, and then we solve for b. So let's do that. So h naught is equal to b exponential minus alpha over a t naught plus r over alpha. So it means that b is equal to h naught minus r over alpha times the exponential e to the plus alpha over a t naught. And now we know b, we can substitute back to get the final solution with no arbitrary constants. So the solution is h of t is equal to b, which is this, h naught minus r over alpha exponential minus alpha over a t minus t naught plus r over alpha. So you can see that in the limit where t gets very big, so that t minus t naught is a very big number, the exponential is going to decay to 0. So this first term will die away and will just be r over alpha. So r over alpha, that's the steady state solution. So steady state I guess right, so if the exponent is very small, so if t minus t naught is much bigger than a over alpha, this will be a very big number. If this is much bigger than that, and the whole thing will decay away to 0, or as t goes to infinity, then we have h of infinity goes to r over alpha. Whereas at time t0, then t naught minus t naught is 0, the exponential becomes just 1, and we have h naught minus r over alpha plus r over alpha, and we just get h naught, which is the initial condition. So the solution will look something like this. It will depend on whether h naught is bigger or smaller than r over alpha. So if this is r over alpha over here, then if the solution starts off bigger than r over alpha, it will decay away towards the equilibrium. If it starts lower, it'll approach from below exponentially towards the equilibrium solution. So all the solutions will converge to the steady state. And the e-folding decay rate is going to be given by alpha over a. So the time scale to approach is a over alpha. So a over alpha, tau equals to a over alpha, is the e-folding decay time scale. So every time t increases by tau, this the deviations from the final steady state solution decreases by a factor of 1 over e. All right, now we want to look at how we would solve the solution numerically using either Euler forward or Euler backwards. So let's do that. So this is page 1, page 2, and let's do a numerical solution. All right, so the discretizing in time, we have h at time step n minus h at time step n minus 1 divided by delta t is equal to r over a minus alpha over a h and n minus 1. So this is the Euler forward in that we evaluate the time rate of change at the left side of the time interval. So if this is time and we're trying to go from here to here, this is delta t, we take the time rate of change value at this point to advance the solution to the next time step. So the time rate of change that is evaluated here for Euler forward. For Euler forward, we evaluate the time rate of change at the beginning of the time interval. So that's for forward. If we were doing for Euler backwards, we would evaluate it here. So by contrast, if I do the Euler backwards, we'll have h of n minus h of n minus 1 So the only difference is that here we use time step n, and here we use time step n minus 1 to evaluate the time rate of change. And then after that, it's just a matter of solving for h of n in terms of everything else. So h of n is equal to h n minus 1 plus delta t and this can be further simplified into the following form. And then for the Euler backwards, we solve for hn. We'll get hn is equal to hn minus 1 plus delta t r over a minus alpha over a h of n. And if we bring in all the hns to one side, we'll have 1 plus delta t alpha over a h n is equal to h n minus 1 plus delta t r over a. And then we can divide both sides by this prefactor to get the solution. So h of n is equal to 1 plus delta t alpha over a to the minus 1 h n minus 1 plus delta t 1 plus delta t alpha over a to the minus 1 r over a. So the solution is similar in form. We have this prefactor multiplying h minus 1, but this time they're the same, except this one has a plus, this one has a minus, and this one is raised to the -1. So this factor here is a little bit bigger than 1, but then when we take the reciprocal, it becomes a little bit less than 1. And in this one, the prefactor, depending on the size of delta t, will be a little bit less than 1. And so this will be, both of them are pre-multiplied by a factor which is a bit less than 1. But the factors are slightly different. And then we have the rest of the solution, where in this case, it's just r over a times delta t, but here we have this extra prefactor multiplying r over a. If we compare these solutions to the analytic one, right, one thing that's absent in this solution is the initial condition. But it's in here in the sense that to go to time step n from time step n minus 1, we needed to know h at n minus 1, and if we didn't know that, we needed to know h at n minus 2 by repeatedly applying this formula. And so at some point you have to stop looking at previous times, and that's when you use h naught. So you start the whole scheme by putting h naught, and you get h1, and then you know h1 in terms of h naught, and you can solve for h2, and so on, and you can step forward. And it's the same thing for the one down here. Right, we need the initial condition h naught to get the whole scheme started, and that's where the initial condition will be specified in terms of the time stepping approach. So let's set it up and compare. We'll code up these two schemes in MATLAB, and we will compare them to the analytic expression over here. All right, so over here, tank with source and sink. So the source R, let's pick it to be 1 liter again per second, meters cubed per second. The flow out alpha, we'll pick it to be 0.001 meters squared per second. And so we can see that the steady state here, which is just r over alpha, will just be 1 in this case because I cooked the numbers to just give me a steady state water height in the tank of 1 meter. But if I change these numbers, we'll get a different balance between for the steady state. And then I'm going to code up initial condition. So T naught, let's say we'll start at 0. H naught, let's start at 2 meters, for example. And then the analytic solution, H analytic, is going to be a function of T, which is equal to H naught minus R over alpha times exponential function minus alpha divided by A. I have to specify what A is. Star T minus T naught plus R over alpha. And for A, let's assume that it's got a cross-section area of 1 square meter. And let's plot the solution right now to see what it looks like. So T is equal to 0 in steps of 0.01 to the time scale I said is alpha over A. So it should take about, A over alpha, which is about 1,000 seconds to reach steady state. So maybe I can take a time step of roughly 1 second and go up to 3,000 seconds. And now we can plot T, HA of T to be here. All right, so this is a solution. We started off with the height at 2 meters, and it decayed down to, it's approaching 1 meter, which is the steady state. Let's pick a bunch of different initial values and plot the solutions for several initial values. So if we do that, we will have, let me make this a little bit longer so it decays better, 5,000. And we will do a few solutions. So I'm going to add H naught and T naught as initial as parameters to HA. H naught and T naught. H naught is equal to 0, 1, 2, let's say 3, or no, let's do it in steps of 0.1, 2, 2, yes. The T should come first. And so here we see all the solution. Let me make it big. So if we start off at 0, it increases exponentially because the inflow is bigger than the outflow until it starts slowing down until the outflow exactly balances the inflow, and then you're at steady state. And if your height is higher than the final steady state, then the outflow is stronger than the inflow, and then the volume decreases up until the point the outflow matches the inflow again and you're at steady state. So that's the dynamics. This is an example of a system with a feedback, in that the height of the water, if you're is above the equilibrium state, then there's a restoring force to bring you back towards the equilibrium height in the tank. Whereas if you're below it, there's a feedback that pushes you back towards the equilibrium. So it's called a stable system with a feedback. All right, now we want to solve it using the Euler forward and the Euler backwards. So let's do that. And I need to specify a delta t. So dt is equal to t2 minus t1. And then for k equals 1 through the length, or maybe 2, we'll start at 2. 2 through the length of t. And the reason we start as 2 is we're going to specify h to be h naught at time t0. So nan, and we will have n comma 1, where n is equal to the length of t, and then h of 1 is equal to h naught. And then we can use our Euler forward to update when we want. So h at time step k is equal to h at time step k minus 1 times, I guess I'll put it the prefactor, 1 minus dt times alpha divided by a plus dt times r divided by a. And then we can plot t and h. Red. Right, so it starts at 2 and then decays until we reach around close to 1 after 5,000 time steps. That was for h naught equal to 2 as the initial condition. Let's do the same thing as what we did for the analytical solution. We'll try to plot we'll solve the time stepping solution for a whole sequence of h naught values. So for h naught is equal to 0 by 0.1 up to 2. This is a constant. I push those out here. Then we set the initial condition, then we time step, and we make a plot. And we continue the loop, and I need to do a hold on after every plot. Hold on. CLF, EX1. Whoops. And so this is the similar kind of solution as before, except now each solution branch has been solved using the Euler forward scheme. If I zoom in, you can see The time step is what is the time step? Is 1 second. If I zoom in, we should be able to see the individual time steps. Right, you can see that each little segment. So it evaluated the slope at this point and slept forward to this point, and from there it reevaluated the slope and advanced to the next one. And it strings out by connecting the dots, by successively evaluating the slope of h as a function of time, and then it can march along. We should maybe plot the solution analytic against the numerical, so I will do that next. And we can look at the discrepancy between both. CLF, Ux1. And so we have a very good agreement between the exact analytic solution and the numerical solution. The exact one is the blue line, which lies on top of the circles. If we make the time steps smaller, then we will have a less accurate answer. Let's do that. Let's suppose we pick a time step of 100 seconds. And here for the analytic, I'll use the finer resolution, 0 by 1 to 5,000. So when we do the numerical one, we will have a finite time step of 100 seconds, so there will be a bigger error, and then we'll see how good the scheme does. So this time we can see some discrepancy, so the time steps are pretty far apart, and the exact solution and the analytic solution don't agree anymore. Let me zoom in so you can see. So when we're close to the equilibrium, the fit is not too bad, but when we're farther, it's worse, and it's worse where there's more curvature. So let's zoom in a little bit on these. Right, so the numerical solution, which is these piecewise linear segment, seems to overestimate the concentration, or seems to overestimate the height of the water in the tank compared to the exact analytical solution. They're all a little bit lower. And on the other hand, when we're approaching from above, it's the other way around. The analytic one has a water level which is a little bit higher. Now we're going to modify the code and replace the Euler forward time stepping scheme with the Euler backward time stepping scheme. And I have the schemes over here. So remember, the only difference is that now we evaluate the time derivative of the height at the end of the time interval. And so what happens is we need to manipulate the equation to solve for the height at the end of the time interval, and we have to invert this quantity here, 1 plus delta t alpha over a. In this case, since we have a scalar equation, finding this inversion is just finding the reciprocal of this scalar quantity. Later on, when we do systems of differential equations, then you will see that we'll have to invert a matrix in order to apply the Euler backward time stepping scheme. So the scheme, now this minus sign becomes a plus, and what used to be multiply is now divide. H at k minus 1 plus delta t, and then this divide applies to both h and delta t times the forcing. Make the plot, and then the analytical. So let's run it. And this time, let's make a zoom. We still see this error, but unlike the Euler forward case, now when we're approaching the equilibrium solution from below, the numerical solution has a lower height than the analytical one, and on the top it's the other way around. the numerical solution is higher than the analytical one. This is the opposite of what we saw for the Euler forward case, and it's fairly easy to see why that is, right? If I look at the difference between the Euler forward and the Euler backward, if this is the true solution, the analytical one, and we are going to step from here to here, the Euler forward calculation evaluates the slope at the beginning of the interval, where the slope is steeper for this particular solution. And the Euler backward evaluates the slope at the end of the interval, where the slope is flatter for this particular solution. And this is why the Euler backward seems to decay more slowly than the analytical solution. Is because the slopes are always underestimated with the Euler backwards. For the Euler forward, it was the other way around. The slopes were always overestimated.